what you already know, and that's what math is. We're going on from what we learned in the last section about exponentials, and we're going to see their relationship to their inverse functions of logarithms. And inverses, if you remember, we were in that section explicitly. Inverses just switch out the x and the y. So it's not too difficult to see their relationship if you just give your brain a chance, okay? So in exponential form and logarithmic form, they're inverses of each other. Now, thankfully, the vocabulary isn't too difficult. And I've got the screen up because I'm going to write on the board. Maybe I can pull it down next. I've got it already drawn over here, the relationship. It's kind of covered up there. The relationship between an exponential, I'm going to have to rewrite it. This is the one we just learned. Exponential growth function. Getting closer and closer to zero, not quite reaching it. And this is the new one we're learning today. Okay. Where the y's go to negative infinity. I'm sorry. Yeah, the y's just go up and down forever. But the x's have a boundary here. Here the y's had a boundary bigger than 0. Here the x's have a boundary bigger than 0. Okay, and remember, inverses are like symmetrical across the y equals like x line. So that's what I tried to draw there. For better or for worse. And we'll see that in the homework. It's just this note gives you about the equation. It doesn't have you draw the picture of the function yet. Okay, so in exponential form from module 13, b was the base, and so for the inverse, we call this the base of the log. LOG, logarithm. That means I have a problem when I don't know the exponent relationship between the base and the output A. So I put it inside a logarithmic function to get out the answer as an exponent. Okay? So the answer to a logarithmic function is the exponent. The answer is an exponent. That's why logarithms were created. Because I might have missing exponents where I can't, it's not a whole number. And so on our calculator, we've got a couple of common logs. One is log base 10, the other one is log base e. If you notice, their inverse functions are the second functions above them. If you have a Casio calculator, that will calculate the log base anything. So you're a couple of steps ahead from the rest of us that use the yellow calculator. But you can still use the yellow calculator to find the answer to log base anything. So there's the game, guys. The game you're going to play. Okay. You're going to change an exponential equation into logarithmic form. That means the b, big B of the exponent turns into the little b of the log. The answer to the exponent becomes a part of the problem in the log. So notice that where they live. And the exponent becomes the answer. So the answer is an exponent But I ranted and didn't write. The answer to a log problem is an exponent. So for me, when I'm writing from a exponential form to a log form, I put the little b down. I put the exponent out on the other side of the equal sign. And then those are the only two I have to remember. The third one goes in the missing space there. Okay. I would write the 81 last, just because that way I only have to remember two things. The base of the exponent becomes the base of the log. The exponent of the exponent becomes the answer to the log. Then I put that third number where there's a space left. So you make up your own game, whatever, and that's what it is. It's a memory hook. Okay? And the reason is the definition of a logarithmic function is to find missing exponents. We get to use technology. You guys stand on those shoulder of giants, and it's just within my lifetime, this technology's been made available. Because as a high school senior, I got to use tables in the back of my math book for common logarithms. Okay, this was my resource. Okay? So, it's that short of a time. You guys have so much. So much. Just amazing. The numbers didn't change. It's just how you got them changed. I read a table, you get a punch a button. Okay? But there's always a discovery piece in there. What would the exponent look like? If this was the base and this is the answer, what would the exponent look like? That's what you've got to keep you on your toes. You've got to use some common sense. Numbers, right? So obviously you can check in your calculator what power of 3 gives us an 81. That's what we did on the last lesson. Okay, now we have technology. If it's not like what power of 3 gives me a 12? There's no power of 3 gives you 12. Oh yes, there is. It's you know, it's like a rational number. It's like, you know, it's decimal. So like 1 point something, so, or 2 point something, I guess. So because it's over 9, but it's less than 27, you can play that game too. All right, this is what I do when I'm going from log to exponent. Show you my little path I draw in my head, and then you could do it with your pencil as well. Oop, 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 oop. I'm using the wrong buttons. Hopefully I didn't bust anything. I want to zoom in so you can see my pencil marks. If I'm given this story, I circle my base, I point to my exponent, and I come a ring around the rosy to my result. So 5 to the third is 125. See that? 5 to the third is 125. That's a relationship between those three numbers in a logarithmic function. Just trying to save you some time instead of you guys just staring at that picture and thinking, where did that come from? What does that mean? How do I know? You know, this is the relationship between those three values. I think in the homework they have you rounding to the nearest thousandth. Some of the homework might be whole numbers. I think that's what this worksheet is all whole numbers. You know, you don't have to calculate a decimal value. So you should be able to go either way. Base to the power is the result. Log of the base equals the exponent. Okay. So let's write these exponential equations in log form. So just like I said, I write my log first because that's abbreviation for logarithm. I write my base next because the base of the exponential form is easy to find. My answer is my exponent. And then if I ring around the rosy, 64 goes in the missing pocket. So this is new. I'm assuming nobody's ever done this unless you did it in like ACT prep. So it's a language. It's like learning to spell a new word, learning a new vocabulary. Okay, you got to give your brain some practice. That's how things change. So I write my word log. I put the base of the exponential equation. I have it equal to the exponent, and then I pop my third number in there. It's frozen. There we go. Okay? See, 4 to the negative 2 is 1/16. Remember, negative exponents create those fractional answers, right? If you put this in the calculator, you get out. Negative exponents make reciprocals. You know, not necessarily fraction answers. It just depends what you start with. Negative exponents make reciprocals. Write the word log. Put the base. You see it's a fraction. The answer is the exponent. Oh, we can't see, sorry. So my missing part of this logarithmic form is my 127. This is subscript. And you'll use that subscript button on your homework. You feeling it? Keep good notes, make good memory, make good practice, make great game. Okay, this is where I do the loop-to-loop. Write the logarithmic equation in exponential form. I circle my 7. Raised to the second power equals 49. Common sense, right, guys? Use your common sense. Well, I'm not sure. Try it in your calculator. If you accidentally misplace these numbers, you're going to get a false statement. Around the block, around the clock, right? Counterclockwise. Okay. Circle the 2, point to the negative 4. It should give me a 1/16. 2 to the negative 4 is 1/16. Because the negative exponent takes a reciprocal of 2 to the 4th power. So they start you out. Simple, simple. Okay, circle the 8, point to the x equals 48. 8 to the x is 48. Now that one, yeah, you can't check. Right? We could check on Desmos for sure. Congratulations. Exciting time. Do you need a paper? We're just almost done with this one. Just got a couple more, then we'll get into the homework on that. Or on that iPad. Talk about how Desmos helps us with graphs. Okay, so here is how you evaluate logs from what you know about exponents. So we're not using technology yet, only to check our knowledge. Let me zoom out of it a little bit. So they use question marks. I'm going to go ahead and say equals what. So that's what they're finding is this question mark here. So they said 4 to what power is 64? And so you can test numbers Therefore, the answer to this question is 3. So that's how you do it when you have a nice number. So you just have to check and see, does 4 to the third power equal 64? Yes, it did. So the answer to my question is the exponent. Remember, the answer to a log question is an exponent. So here, 2 to what power is 1/8? Well, because it took the reciprocal, I know I'm going to have a negative number, a negative exponent, and then 2 to the third is 8. So that's why through guessing and checking, or testing and checking more or less, that's why the result is a negative answer. And your calculator will tell you so, right? Just to verify your thought. So that's good when your answers are whole numbers or negative numbers, or rational numbers. Pretty simple. When things need rounded and such, technology needs to be kept in. Okay, so I'm going to go ahead and say this is equal to x. So I'm going to solve for x. So I put 5 to what power is 625. So get my calculator out. 5 to the 5th. Whoop. Oh, you can't see. Here we go. 5 to the 5th. Give me 3125. Too much. So back off. 5 to the 4th. There we go. 625. So x equals 4. Remember, the answer is the exponent. You're finding missing exponents. Okay, here. Am I still on the screen? Yep. Ooh, 8 to the what is 2. So I've got to have a small exponent, like a root, because this is not growing. This is decaying. So my answer is going to be like a fraction. So I take 8. Now I know what the answer is. That helps. But I also know that since 2 cubed is 8, 8 to the 1/3, if you remember from our exponent lessons, well, is like taking the third root of 8. So my x is a fraction. So if you see that, this is a great example. If you see a beginning base that is larger than the ending answer, your exponent is going to be a fraction to make things decay. Okay. This one, 3 to what power gives me a reciprocal of 3 to a power, so its x is going to be a negative, and then its 3 squared makes 9. That's how I know what it is. I flipped it with the negative, and then I saw how many factors of 3 give me 9. And I can put it in my calculator to check it out. If you're not sure, enter that in the calculator. Okay? Oh, you can always check your work. Yay, yay, yay. That's what I love about algebra. Okay, let's go to our HMH. Mark this period 5. Okay, I'm going to hand this off. Okay, you just put out actually when you're done. And I printed them out so I can film them here. If I can find my story. Here it is. And this is where they're going to take a deep dive for a couple of questions about what the graph looks like when you're graphing a log function. versus an exponential function. So that's where this stuff comes in. Our log function looks like this guy. I don't know if you remember our parent functions we wrote about a couple weeks ago. We had, oops. This is a natural log function. This is log base e. But you see what it's doing? It's getting closer to 0 for the x instead of the y. Here, this was getting closer to the 0 for the y. So these two are inverses of each other. They're not on the same graph, but that if I laid one on top of the other, then you could see their relationship symmetrical across the x equals y axis. Okay, so you're going to tell the story that you all know how to do very well about this picture. So the domain of the x numbers, and it looks like they're getting closer to 0, but they don't go to 0. Oh, thank you. And let me maybe write it in a darker color so you can see. Maybe a purple. That's me. You can do you. Okay? You're typing it in, right? So x is greater than 0. Okay? So you have to type in the x and the greater than sign from not from the blue pad, but from your keyboard 0. Because it's just getting close. It doesn't go back. And I can zoom out a little. Maybe then you could see the whole question at once as far as sideways goes. So since it's the inverse of exponents, the domain has a boundary of greater than 0. The range, see how the y's go from negative infinity to positive infinity? This looks like it stops going up, but it never does. It just slows down. Okay? So the range is negative infinity. Don't forget, we're talking y less than y, which is less than positive infinity. You get those from your keyboard, your blue keyboard. For the infinities, you have to type in the less than. Okay? We need more time? All right. So as x goes to the right, my curve is going up. So that's positive infinity. As I go closer to 0, my curve is going down. Negative infinity. See how I go left, going down. The reason why they have a plus, this is, say, coming from positive going to 0. That's calculus talk there. Okay? You'll see that in calculus when you're working with limits and when a function is defined. All those things. You get to do that again. That's why I want to get to as many as I can basic. So when you see them again next year, which you will, you'll know at least what they look like. Okay, the only place it crosses the x-axis is right here, where x is 0. Or, I'm sorry, y is 0, x is 1. Okay, the x-intercepts y is 0, x is 1. They didn't want the ordered pair. They just wanted the value of x. And so you see how it's getting very close to the y-axis, but it never touches it because of taking the log, the nature of the function, taking logarithms. X can be 0, but y cannot. Well, y can be. Sorry. Y can be 0, x cannot. Because I can never if I take a log of a 0, it's undefined. Because, yeah, there's that. Let me see if I can do that. I'll show you in the calculator. Just the natural log of 0, domain error, undefined. Take the log of 0, clear. Log of 0, undefined. Okay? If you have a Casio that you can put in any base, log base, whatever, there's no such thing. That's why there's no y-intercepts. Okay, the graph has what's stopping the x's? The y-axis. Remember, asymptote's the no-no line, and this curve will never go past the y-axis without, being transformed. So I don't know if you remember how to type intervals. So if I'm looking at this guy and I want to know what part of this function is negative, what part of the x numbers are negative, from 0 to 1, but it doesn't include them. So the interval, you have to put a parenthesis, 0, comma, 1, close a parenthesis. Because that's when my curve is under the x-axis. So you get fractions. Fractions demand negative exponents. That's what we're saying. Okay? And when is the exponent positive? That is, see, I can do the green thing. After 1 to forever. I run into infinity then. So how do I write that interval? Parenthesis after, no, mistake. After 1. Parenthesis, positive infinity. Parenthesis. It doesn't include 1. Okay? Because I'm looking for positives, not zeros. It's the green part of the function. And the function is, what direction is that curve going as you read it like a book? So without any transformation, the function never decreases. And that's our graph game about log functions. We'll finish the rest tomorrow. Then you'll have 15.1 for your very amazing, long, fantastically wonderful holiday.